All right, today we're going to be talking about Bayesian linear regression. So suppose we have some data, pairs of x's and y's, and suppose we have n of these points, I equals 1 to n, and suppose we have where each xi is an m-dimensional vector and yi is a number. The advantage of Bayesian linear regression is that it allows us to encode our beliefs about what we think our weight vector w should be, and it then allows us to obtain a posterior distribution over that weight vector instead of just a single point. Now, Bayesian linear regression assumes that yi, each point yi is generated according to some normal distribution with mean w transpose times xi and then some variance beta inverse, where beta is known as, this is known as the precision parameter, because the higher your precision, the lower the variance and the more certain you are about where exactly your y will be given some x. So this is what Bayesian linear regression assumes, and this is known as a generative model. And that's because it assumes that y's are generated in a particular fashion. It says it knows how the data is generated. So you can calculate the probability of yi given some xi and some weight vector w by just taking the normal of yi given xi w. This should be a comma. Whoops. Whoa. Didn't mean to do that. Get the eraser. So you can calculate the probability, and that's just equal to take the density of the normal PDF times e to the negative beta over 2 times the square of yi minus w transpose xi. And this is known as the likelihood of that particular point. But for linear regression, we're always interested in the likelihood of the data overall, not just one point. And for that, we'll use vector notation, and we'll say that the probability of all the y's given all the x's and our weight vector is distributed as a multivariate normal, where each individual data point has a variance, so we'll use beta inverse times the identity matrix. And what this means is that the data points are uncorrelated. Uncorrelated. We have zeros everywhere except for the diagonal, which is just full of the variance. And so now this allows us to obtain a posterior distribution over w after having seen the data. So remember that with typical linear regression, non-Bayesian linear regression, we just obtain a point estimate. So in the case without regularization, and we just obtain this point estimate. And the main point I'm trying to drill in is that this is just one vector W. But in Bayesian linear regression, we can use Bayes' rule to obtain a distribution over W after having seen the data. And we get this by multiplying the likelihood by our prior beliefs about W. So this is fittingly called a prior. This is what we think W is before seeing the data, over the probability of the data, which just ends up being a normalizing constant and does not depend on W. So this is known as, again, the likelihood, and then this is called the posterior distribution. All right, so it turns out that we often encode PW as a normal distribution in and of itself. So a common choice is that PW will be normally distributed with some initial mean and some initial covariance matrix. And it turns out that if this is the case, and if the likelihood is the case, then probability of W after having seen the data, the posterior, is also normal. This is also normally distributed. And I'm going to go through the derivation of that in a second and show why that's the case. It gets a little bit tedious with the math, so if you're not interested in that proof, you don't have to follow along. But before I do that, I just want to say a couple more things about Bayesian linear regression. And that is two things. First, if you have a new data point, x star, let's say you've trained your model and you have a posterior distribution already, the way you would obtain a prediction on that new data point, you could do the following. You could integrate over your entire distribution of W, your entire posterior, and just take the value of the regression at that point. So that's one way. The second way is, and this would not incorporate uncertainty in your prediction, you could just take the most likely W, the maximum a posteriori W, and you could transpose that with your new point. But this option above allows you to incorporate uncertainty into your prediction. So that's considered one advantage. The second point I want to make is that with Bayesian linear regression, we don't just obtain some y value, but we're actually able to obtain the probability of a y value given some other point x in our W. That is, you give me an x, I don't just give you back a y as in normal regression, but I can actually tell you the probability over many y's. And the way I would do that is, again, integrate over W, integrate over your posterior distribution, and we would just take the probability of that y given x W, and we remember that we said that y was generated according to a normal distribution. So this allows you to not just incorporate uncertainty in your prediction, but it allows you to obtain uncertainty I should say, probabilistic output. And that might be useful for some decision-making problems. So now, at this point, I'm going to go into the derivation and talk a little bit about why the posterior is normally distributed. And we're going to show that that's the case mathematically. So if you're not interested in this proof, feel free to just stop watching. If you are, you can follow along. So let's write a couple things by way of reminder. We want to write the prior PW. We said that that was normally distributed according to some mean and covariance. And so just to be a little clearer about what that actually is, we'll say that that is, and this is just using the normal PDF, square root of 2 pi to the m and then exponent of w minus the mean S naught, and this is just, again, the multivariate normal PDF. So we're going to need that in a second. And let's also write out the likelihood a little bit more explicitly. Probability of y given x, w, and we said that that's also normal. Y given x, w, beta inverse, remember the identity matrix. And let's first write it out as the product over all the points. And now let's write out what exactly that is. Well, here we'll use the normal PDF, one-dimensional again. Exponential of negative beta over 2, and then y minus, so yi, apologies, w transpose xi, whole thing squared. So now that we have explicit derivations for explicit form for the prior and the likelihood, let's turn to the posterior and try to prove that it's normal. So the way that we're going to do that is we're actually going to take the log of the posterior. And remember that the posterior is equal to the likelihood times the prior, that normalized. And so that's going to be equal to the ln of plus, because whenever you put two factors inside of an ln, you can split them up and add the ln of the individual factors, plus some constant. So just to be clear, what I did there was ln of pw given xy equals ln of the likelihood times the prior all over probability of the data. And then by the properties of logs, I was able to split that up. And let's just develop this a little bit more. So let's put the constant out in front. And that constant, again, comes from this guy down here. It doesn't depend on w, so we're not going to be concerned with it for this proof. We're just going to keep it around as a constant. And now let's be a little bit more explicit about what we have here. So this is the ln of 1 over 2 pi beta, just expanding this likelihood term, minus beta over 2. So this is all one thing. And then I take the ln of this guy. So the exponential gets canceled out, and we're just left with what's inside. yi minus w transpose xi all squared. And this is all inside of that sum. Plus, now let's add our prior. ln of, let's look at that first term. 1 over square root of 2 pi to the m s naught to the 1/2. And I'm just going to erase that real quick so I can keep writing. Plus the plus negative 1/2 w minus mu naught. Again, this exponential right here, that gets canceled out when we take the ln, and we're left with whatever was inside. So let's develop this even further, except now we'll rewrite this term, the second term after the k, in matrix notation as k minus, we'll bring out that beta over 2, we'll write it as y minus xw transpose y minus xw, and remember this is how we rewrite the loss function of linear regression in matrix notation. We'll bring this guy into the constant because it doesn't depend on w. And likewise, we're going to end up putting that guy and just treating that as part of the constant because it doesn't depend on w. So let's grab that last term now. Minus 1/2. I'm just going to copy it. W minus mu naught transpose w minus mu naught. Okay, so let's continue just a little bit more, try to get this into a simpler form. So I'm actually going to say that this is 1, k minus 1/2, and I'm going to rewrite it like this, which will be helpful. Let's FOIL out this product. W plus w trans. Now I'm going to rewrite the second term a little bit differently. Minus 2. I'm going to write this as w transpose S0 inverse mu 0 plus mu 0 0 inverse mu 0, and we notice that this also does not depend on w, so that will get absorbed into our constant, as will this term as well. So finally we can rewrite the log of the posterior as k minus 1/2 w transpose. And now I'm going to write something, and I'll justify it in a moment. It's not inverse plus beta x transpose x, close parentheses, times w minus 2w transpose S0 inverse. If I say S0 or S naught, it's because I can't make up my mind. Plus beta x transpose y. And that's all inside the parentheses being multiplied by 1/2. Now you might be wondering what I did if it doesn't immediately jump out to you. I refactored this because it will be useful, but just to justify it, if you look at the line above, everything that comes after a w transpose and before a W. So you can see S0 sandwiched in there. And you can also see that a beta X transpose X comes between a W transpose and a W. So that justifies the first term. And now the second term, we did kind of a similar thing. We just refactored, brought out a W transpose. So we get this guy right here, and beta X transpose Y is a refactoring of this. So I want to pump the brakes on this and kind of just summarize what we're doing right now. We're taking the log of the posterior distribution over W, expressing it in terms of the data in our prior, and we're going to see that it matches a normal PDF. So we're going to see that in a second, but real quick, I just kind of wanted, the way we're going to get there is to use a trick. And the trick is to temporarily stop and just remind ourselves what pattern we're looking for. So let's give ourselves a little more room here. The pattern we're looking for, we're assuming that, so we can say that if the posterior is normally distributed, like we're trying to show, according to some posterior mean and some posterior covariance, then we should expect the ln of the posterior distribution to be equal to it should look something like this. Transpose and it's going to have some constant, because remember there's a constant out in front of that exponential term on the normal PDF. And if you don't understand this, you can just take a look up. Like a couple minutes ago, we kind of went through that, and you'll be convinced that there is a constant involved. Let's just expand this out a little bit more, and we're going to try to get a pattern that matches what we're doing here. So -1/2, and I'm going to expand this like this. Posterior mean, which we don't know what it is yet, but this is the form that it would take. And don't forget the constant. And we notice that this is part of the constant because it doesn't depend on W. So we're just going to absorb that there. And we get our final form. And let's notice that these guys are actually the same. So we'll collapse them into one by just putting a 2 in front. Plus our constant. And now notice that actually we do have a match. This form matches the form we left off on. And to make that clear, you'll see that we have, the pattern is W transpose times some matrix times W minus 2 times W transpose times some other matrix. And that other matrix is, or that other vector I should say, it's not necessarily, it's not a matrix, but this is a vector. So minus 2 times W transpose times this vector. So let's make those equal and see what we get. So we know that if we're just doing pattern matching, the inverse of the covariance matrix for the posterior distribution is equal to S0 inverse plus beta X transpose X. And we know that this product is equal to 0 inverse mu0 plus beta x transpose y. So since we have a pattern match, we can say that posterior W given the data is normal, where the covariance is equal to the inverse of that, and the mean is equal to, just by a little bit of linear algebra, we'll move the covariance matrix to the other side. Oh, this is a pretty bad transpose. Let's fix that. And so we have our results. We've proved that if your likelihood is normal and your prior distribution is normal, you'll end up with a normal posterior distribution over your weights, where your mean is a function of your original covariance beliefs and your original mean beliefs plus your data, and your current covariance. And the current covariance itself is a function of the previous covariance matrix and your input x. So there we have it. Thanks.